Hi students, so today we begin math question bank 19. Today we are going to look at 5 different questions on Laplace transforms. Laplace transforms are very important concepts in mathematics, particularly in control theory, in the solution of differential equations, and in figuring out the stability of any dynamical system. So let's begin. I'm Dr. Ganguly. So the first question, which is the most popular one, is to find the Laplace transform of the unit step function. Now, the unit step function is essentially defined as ft equal to 0 for t less than 0 and ft equal to 1 for t greater than 0. So, if we plot this function ft with respect to t, it's simply going to be 0 all the way to this value here, and at t is 0, it's going to suddenly change to 1 and then continue like this for the foreseeable future. So this is a function which is pretty important as far as different aspects of vibration are concerned, different aspects of dynamical systems as well as signals and systems. So it comes every now and then. Now to find the Laplace transform of this function, we have to look at the definition of the Laplace transform. So the Laplace transform of a function f of t is defined as the integral 0 to infinite e to the power minus st ft dt. So this is the equation or definition which you need to commit to your memory if you are going to solve any problem to do with Laplace transform. Now let's look at the function here which I have given in red. Now of course you see here that the portion where t is less than 0, there ft equals to 0, and so that's not going to be very useful for this integral calculation. What is important is the portion where t is greater than 0. So essentially what we do is we put in ft is equal to 1 because the integral bounds are 0 to infinity, and in this particular bound the value of ft is equal to 1. Now of course I can very quickly do the integration for this function. So it's going to be e to the power minus st divided by minus s, and the bounds are 0 to infinite. Now we need to figure out the values of this particular quantity in this bound. Now what we can do is remove the portion 1 by negative s outside. So we bring minus 1 by s outside, and so inside this we have 1 by e to the power s into infinity, and then minus 1 by e to the power s into 0. So you can clearly see here that here this particular term is going to become 1 divided by infinity, and the second term is going to become minus 1 because e to the power 0 is simply 1. So once we have that, we can immediately write that 1 divided by infinity is going to be 0, and therefore I get the value as Laplace transform of ft is 1 by s. So this is something to remember. This is one of the simplest Laplace transform questions you can ask because the integration is very easy. It involves the integration of the function e to the power minus st, which many people know. Now this particular step is important to remember, and sometimes you can ask questions related to this because how these particular terms become 0 and 1 is important to keep in mind. Now Laplace transform questions are not only useful to figure out things about whether they know this or not, but also if you are asking any type of calculus question related to definite integrals, integration by parts, and so on. The right way to ask these questions is through the Laplace transform because that is at the college level. And of course, if you are a high school student, you will know one of the reasons you study a lot of these particular integrals out there is because you want to figure out how to calculate Laplace transforms later. So let's turn to question number 2, and this is find the Laplace transform of the ramp function. So the ramp function is defined as ft is 0 at t is less than 0. So that's this part here, and then ft is equal to at, t is greater than equal to 0. So that's this part here. Now of course the slope of this line is going to depend on the value of a here. So this is the function which again is very important in many dynamical systems, vibratory problems, and so on. So we are now going to find the Laplace transform of this ramp function. To do that, again we simply write down the function here in red, and then we invoke the formula for the Laplace transform. So again, remember, we use this L here. This is calligraphic L. This is widely used to represent the Laplace transform. So again, what will happen here, because the integral is from 0 to infinite, the part of the function which is defined at t greater than equal to 0, that's going to become active, and so I'm going to get at here in place of f of t. Now looking at this integration problem, you know this is something which can be solved by the integration by parts formula. So if we look at that, we have a function here at, that's the first function. We have the function e to the power minus st, that's the second function. So now let's try to calculate this particular integral. So we can use the formula first function into integral of second minus integral of differential coefficient of first into integral of second. So what will happen here is that in the case of this term here, it's simply going to be at, that's the first function, and this e to the power minus st is going to give me e to the power minus st by minus s when I perform the integration, and the bounds are going to be 0 to infinite. Then again here I have the differential coefficient of the first function, which is simply going to give me a, and then here I am going to get e to the power minus st by minus s. Now I can further simplify this. So in this particular term here I can take out negative a by s, which I do, and so I'm left with t divided by e to the power st. This is from 0 to infinite. If we look at the second term here, again I can take out this as and the sign will change, so I get plus a by s, and then e to the power minus st will give me e to the power minus st by minus s when I integrate that function. So again the bounds are 0 to infinite. So now let's try to further simplify this here. So again here I have minus a to the a by s here, and then if we want to calculate the bounds here, what I have to do is I can realize that if I put infinite on this particular term, then that's going to give me something of the form infinite by infinite. So again I can look at it in the limit. So I can say limit as t tends to infinite, t divided by e to the power st minus 0 by e to the power s0, because the second part is quite easy to calculate. Now of course here you are going to get 0 divided by e to the power 0, which is 1. So this is going to be simply 0 here. That is, this term here is going to be 0. Now let us look at this term here. That's going to give me a negative a by s square, and then again I'm going to get 0 minus 1. Recall the integral we did previously. So you have the 1 by e to the power st term, which simply becomes 0 when t becomes infinite, and the second term is going to involve e to the power minus s into 0. That is going to give me a 1. So it's going to give me the negative 1 here. So now once we have this, the second term here becomes very simple. It simply becomes plus a by s square. Now if we look at this term here, we have to calculate this limit. So a simple way to do it is use the L'Hopital rule, where I differentiate both the numerator and the denominator. So the numerator becomes 1, the denominator becomes SEST, and so as t tends to infinite, this is simply going to become 1 by infinite, which is going to become 0. So I'll have a 0 minus 0 here. So this term is going to get decimated, and so I'm only going to be left with a by s square. So that's the Laplace transform of the ramp function ft, that is a by s square. Now let's look at the third very popular function which we get in Laplace transform problems, and that is find the Laplace transform of sine at. So again what we have to do here is we have to bring in the definition of the Laplace transform, then we have to substitute sine at here, and then we have to expand it out. Now of course that is a classical way of doing this kind of integration by parts, but we are going to use the complex number approach to do it, because in some cases that comes out to be simpler. So I can write sine at as e to the power iat minus e to the power minus iat divided by 2I, and so that's going to give me this integral here, because I can bring in the e values, and so I will get e to the power ia minus st and minus e to the power minus IA minus ST. Again, the integrals of these exponentials can be obtained very simply. So I get these values, and then what I do is I plug the infinite and 0 on these particular terms, and so I get these particular values. Now when I plug in the infinite terms, I have minus st here, so these will become essentially 0. And so when I plug in the 0 terms, that's when I get e to the power 0, so that gives me the first term here, and I plug in t0 here, that gives me the second term here. And again the signs get flipped, because remember, you are taking the second part of the term here. The first part involves the infinite and the second part involves the 0. So that's how I get this particular term here. Now I can simplify this. For example, I can remove the negative sign here and I can write it as s minus ia. I can again put a negative sign here and write it as s plus ia. And then what I can do is I can realize the fact that this is in the form a minus b, a plus b. So this can be multiplied together and I will get a square minus b square. That's going to give me s square plus s square, s square plus a square, and on the numerator I'm going to get s plus ia minus s plus ia. So I'm going to get simplification here through the cancellation of these s's, and finally I'm going to land up with a by s square plus s square. So this is the formula, that Laplace transform of sine at is a by s square plus a square. So that's something again to remember, because what happens that in many differential equations the solutions come out either in exponential functions or in sinusoidal functions. I think we have done the exponential problem a long time ago. You can check it out in one of the older math question bank problems. Now let's come to some theorems which are very important in solving differential equations. So the first theorem is that the Laplace transform of the derivative of a function is simply s multiplied by the Laplace transform of that function minus f of 0. So this theorem gives a very simple way to actually take the differentiation which occurs very frequently in differential equations and simply replace it by multiplication. So this is something which the Laplace transform does and which is very important for its use in applied mathematics. So of course here fs is simply a shorthand for the Laplace transform of ft. So let's try to prove this particular theorem which I have given out in red here. So again I start with the basic definition of the Laplace transform, and then I do the integration by parts. So I take the first function into integral of second minus integral of differential coefficient of first into integral of second. So with that I now have this particular expression here which we can further simplify. So let's do that. So we can write fs is minus 1 by s. I take this out here, and here I have 0 minus f0. So with this particular simplification, then the second term becomes plus 1 by s, 0 to infinite d by dt ft e to the power minus st dt. So now I have got this equation here, and I can further simplify this equation. So I can write this term here as f0 divided by s, and this term remains the same. Now remember, what I was interested in was the Laplace transform of this derivative, and I do have that particular value here. So I can take the integral term and I can take s to the left hand side, or I can multiply this entire equation throughout by s, and in that case I get this equation in green, which gives me that the Laplace transform of d by dt ft is sfs minus f0. So this is actually the same as the theorem I have written out in red. So this is often known as the differential theorem or differentiation theorem of Laplace transform. Now let's create a problem to put this theorem to use. So the way I have given the problems in this lecture, it's something which you can use one after the other. So in case one problem is done by a student, the next student can be subjected to the second problem and so on. Or you can ask this problem one after the next if you are grilling somebody on Laplace transforms. So the question is, find the Laplace transform of cos at given that Laplace transform of sine at is a by s square plus a square. So this is going to help us figure out how to use this particular differentiation theorem. So you can state that use the differentiation theorem for the Laplace transforms. So now what we do is, what we know is this equation in red, which is the Laplace transform of sine at, that is fs, that is a by s square plus a square. Now if we want to use this information, we can immediately realize that cos at is going to be connected to sine at through differentiation. So if we say ft is sine at, then d by dt ft is going to be a cos at, and then I can write cos at as 1 by a d by dt sine at. So this is the important step, and once we have done the step, things become simple, because now we can turn to this differentiation theorem. So again, this theorem in purple, differentiation theorem, you should commit to memory because it's very important. So now what we can do is we can write the Laplace transform of cos at as Laplace transform of 1 by a d by dt sine at. So remember, cos at is just equal to this term. So all I have done is I have substituted that here. Now this is going to be equal to 1 by a into this whole value, that is this Laplace transform here. So I can bring the 1 by a outside the Laplace transform here, and then I get this here. Now if you can of course prove that through the definition, that's one of the simple proofs out there, and then I get this here. Now once I get this here, I immediately recall that fs is a by s square plus a square. So I can substitute the value of fs here. So I get s into a by s square plus a square, and f0 is going to be sine of 0 because I simply substitute t is 0. So I get sine of 0 here. Now I know sine of 0 is simply 0, so I can remove this term, and so I get the Laplace transform of cos at as s by s square plus a square, because these two a's cancel out, and I am only left with s by s square plus a square. So this is something very important in many situations, this particular theorem, and there are many more theorems on Laplace transform can help you simplify your life. But today I'm going to cover just the basic things in Laplace transforms which are actually amenable to questions you can ask in different interview settings. So with that, we will end the question bank 19. In the next question bank 20, I'm going to further delve deeper into Laplace transform. So we are going to see what happens to the second derivative, how to solve differential equations using Laplace transforms, and also how to find poles and zeros of transfer function, which are very important problems in control theory, in system theory, and in applied mathematics in general.